So, hello everybody. Welcome to the ELE 30 not 320, 302 final exam review session. So, to begin, right, you can find my notes on my website there, of course. So that's, I'm going to be referring to those notes throughout the live session, just for just like those are my notes. And otherwise, there's really not that much else to say. So I'm going to be doing the fall 2013 final from the Rest Bank. But I will not be doing the Laplace question from there because the Laplace question from there is just weird. So I'm going to be doing a Laplace question from the textbook, which is the first thing we're going to do. And then we're going to do the rest of the questions there from that exam. All the rest of the relevant questions from that exam. So let's take a look at what's going on here now. The Laplace question, I haven't tried this one, so we'll be able to get through it, but it's, forgive me if there's any mistake in it, but we'll figure it out. We will get it right. So any questions before we get going? I think probably good, but let me know if there's any questions before we get going. I am recording and your guys' voices are in it, and looks like we're good. Okay, so sounds like we are good to go. So what's happening here is we have a current source. Oh, interesting. It's a current source. I didn't even expect that. Okay. We have a current source, which has an excitation little function here of e to the negative 2t unit step function of t, right? And then the rest of these things are just all regular stuff that we're used to dealing with. So you know what I should do? I should open this up here. So this is, of course, this is from the textbook. And again, that's because the one in the course, in the actual thing, is not very good. Okay, they don't have it. Okay, I've actually never done one with a current source, so let's see if that makes any difference here. So essentially, we want to do this using Laplace because this is in the Laplace section. So what we're going to do is we're going to transfer the circuit into the Laplace domain, just element by element here, and then from there we can take it just one step at a time and just use our DC analysis to figure that out. So to begin, right, we need to know how to transfer all these components into Laplace. So let me find that in my notes here so I can show you guys. The Laplace stuff is right here. It's a little bit difficult with all the Zoom things open, so I will scroll down. Okay, there we go. Actually, you know what? I'll move that up there. Yeah, so no initial conditions. Yeah, that's true. So we got to figure out that first. I guess we'll set it. Is that not given? Sorry, I really should have should have shown someone where there's a Slater solution for it. Yeah, let me get the notes here. I'll open this up. There we go. So in my notes, if you go to page 43 or something like that, we can see how we transform all the elements into different things. So you have a choice of how you do it. You can either do it as a voltage source in parallel or a current source in series. So it honestly might be worth it to try it with a current source in this case because we have a current source there, which would be an interesting one. But yeah, we have that. Alternatively, I could do something else. Sorry for the last minute thing here. Alternatively, could do one like this. Let me check this quickly. Sorry, give me 1 second here. You know what? We might just do a different one. We'll see, because I just want to make sure it's a relevant, like a good question to ask for the thing. So let's try this here. Okay, let's just try it. Let's see what's going on. So whenever you're doing something like this, you do need initial conditions. I guess they're not given. I think they're usually given in the question. Let me just check for another one here. Determine I of t in the circuit by Laplace. Otherwise, we can also just try it by saying...
Initial conditions for these questions is always like nothing.
It's just
I realized that by doing some of them, that if it's a unit function, it just means that before zero, there's nothing there.
So we can take a look at t less than 0 here, right? And that just means, yeah, like exactly like you were saying, right? If this current source turns on, so that would be our first step here for initial conditions. Initial conditions. We're just going to confirm what you just said. So for t less than 0, that source is fully off because there's a unit step function there, right? So if the current is 0, right, if there's 0 current going here, right, that means it's an open circuit, right? We're going to have 0 current there. So essentially, our circuit is just like this, right? Our circuit just looks like this. And essentially, if this is what it looks like before when t is less than 0, you're going to have to forgive my drawings. I've never been able to draw circuits very well. Then that just means that there's essentially no energy in the circuit to begin with, right? At the time that this turns on, there's no energy sources, right? So it's just going to be all of your initial conditions are just going to be 0 in this case, right? There's no other source there. If there was, then you'd have to try to figure out what this was going to be. But at the moment, there's no sources here, so there's no initial conditions. Hopefully that makes sense. So our initial conditions are 0. So then from here, we can just now go ahead and convert this to the Laplace domain. So converting the inductor to the Laplace domain, we can do that just by adding a voltage source in series, or we can do it with a current source in parallel. And I think that actually might be better to do this time. Well, actually, since the initial conditions are 0, we actually don't even have to do that. So the initial conditions are 0. That's all that's going to be. So if you look here at our inductor, right? Where's the inductor? Sorry, here's the inductor. So if you are converting just an inductor that looks like this, oh, you can't see, can you? Sorry about that. I'm going to make that mistake often. So if you are converting an inductor that looks like this, which is just an inductor, into Laplace domain, there's 2 ways you can do it. You can either do it like this, or you could do it like this. And so from here, we would probably want to match it to the actual source. So let's do it with that current source right there. Since it's a current source that is our source here, let's use the current source option. And since it looks like it's all approximately in parallel, looks like that's probably the best option. So we're going to go with this. But notice that the value of this source right here is entirely dependent on the initial value. And since we said our initial values are 0, we don't even have to actually consider that. So we are good. So I can just fully convert this to the Laplace domain by just doing this as SL, so S times 1, which is fine, right? I'll do it in purple here. And then the resistor is just, well, the resistor doesn't change. So I'm not going to take screenshots a million times. You can look in my notes. But essentially, the resistor just doesn't change there. So it's just 2 ohms there. And then here, the capacitor, right? The capacitor turns into so it's going to be 1 over SC. So 1 over S times 0.5, right? So 0.5 is a half. So I'll just put a 2 on the top. So it's 2 over S there for that. And then our source like this, well, it's still a current source like that, right? And that is still going to be our this, but it's going to be the Laplace of I of S of t, I S of t. Right? It's going to be Laplace of that. So let's figure out what the Laplace of it is quickly. Generally Laplace stuff, like there was some ELE Laplace that they told us about, but I think generally Laplace of these kind of things you can do yourself pretty fine.
Sorry to interrupt, but
yes.
I think you wrote for initial conditions 0 t is greater than 0, and I think that's confusing people.
Yes, it is confusing people. Yes, there you go. Thank you. Thank you for that. So to find the Laplace of this, I mean, generally you can just, of course, use whatever theorem you want, but I mean, I like to we can just use a table, right? So I have a textbook that I have a table from, so obviously tables are a good way of doing this. So if we have e to the t u of t, I think that's on the table directly, and if it's not, then we got to use like the transition theorem stuff. We have that here. Let's find it here. Okay, so it appears it's not on the table, so we got to use the transition theorem stuff. Okay, so I'm going to open up my math notes then to do that. So those are, of course, also available. And so we will do that. There we go. Open. And so to solve this Laplace, we are going to have to do probably this. So no, that's fine. This is okay. Step function. There we go. Okay, so we're going to have to, first of all, use this, which is the first translation theorem, right? So I'm just going to move this to the side down here, which is just saying that if I'm taking the Laplace of something with an e to the at on it, then I just essentially say, well, I need the Laplace of the unit step function, which is just 1 over s, if I'm not mistaken. Yeah, which is just 1 over s. I'll just check that here, but it is just 1 over s. I just don't want to say the wrong thing. And then, just find it here. Yeah, that's fine. So t minus 0. Yeah, it's just 1 over s. So then all I do is this is just going to be 1 over s, but just evaluated at s plus 2, right? Because it's e to the at is f of s minus a. So minus 2 is going to be plus 2 here. And so then this is just going to be 1 over s plus 2. That should be fine. Yes, that looks good to me. Okay, so that is going to be our Laplace. So then I can take the whole circuit. Hopefully someone can confirm for me that that is a correct Laplace.
That's what I got as well.
Yeah, that's what I got.
Okay, perfect. Thank you. So now I'm going to take the circuit, and I'm going to just replace that with the Laplace of the thing that I got. So it's 1 over s plus 2, and that is our current source there. And so the thing that we're looking for is going to be that current, like that, right? Current in that loop like that. So let's see. Yeah, that's I0 that we're looking for. So to find that current, well, there's a few ways we could do it. Of course, I could find, let's see, it might be worth it to do just a quick nodal, because we just find the voltage at that node up there, and then we would find this is ground, obviously, and then if we know the voltage there, we can just use use that voltage to find it here. So I think that probably is the best thing to do. Yes, thank you for confirming, Ethan. So we're going to now use nodal to find this voltage here, which I'll just call V. I'll just call V, because we only have one node. So I'll just do that there. It's convenient when things are in parallel, you only have one node there. So we will set that to be the ground. I'll do it in this color, right? And then let's just quickly do a little bit of nodal here, right? So the current coming in, so it's going to be negative 1 over s plus 2, right? Plus, that's just an s. So I'm going to be clear here, actually. I'm going to draw my s's with little things like that, because obviously they look like 5s. So let me draw my s's with those things. So that's just going to be, okay, plus, so v over s, right? Plus v over 2 plus v over 2 over s equals 0. Okay, so to note here, v over 2 over s is equal to our I0 that we're looking for, right? That's the current there. It's this one right here. But then we're going to use this to solve for v. Right? Okay, so I'll start solving a little bit here. V, we get 1 over s plus 1 over 2, okay, plus s over 2, right? That term just turns into s over 2 when I factor out the v, okay, equals 1 over s plus 2. So any confusion about how I did that step there? Any confusion? Okay, let me know, of course. At any moment, you can let me know. We can talk about it more. But yeah, there's that. Okay. So now we're just going to continue solving. So I guess I'll make things a common denominator here. So this is going to be 2 over 2s plus s over 2s plus s squared over 2s, right, in a bracket, equals 1 over s plus 2. V equals 2 plus s squared over 2s. V times that equals 1 over s plus 2. And then v is equal to now this. Okay, so v is equal to, well, I'll just write it like this. 1 over s plus 2 times 2s over 2 plus s squared. Okay. And essentially, we got to take the Laplace inverse of this, right, to figure out our v. Well, so to figure out our v. Oh, so we don't actually even have to do that, because we can just multiply it essentially. So let me write that here. We can just essentially multiply it. V is equal to s over 2, right, just by doing this. So if I just take this v value and just multiply it by s over 2, right, I would have my I value, right? So I'm going to do that. And then I'll take the Laplace inverse of that just so that we get it all done in one shot there. So I will then say that, okay, so I'm going to note here that I naught equals V times S over 2, right? So I naught is equal to 1 over S plus 2. Wait, can we not just sub in I naught before isolating? Yeah, that's what I'm doing now, I think, right? That's what I'm subbing in I naught now. 2 plus S squared, right? Times, and then I said, yeah, it's going to be S over 2, right? S over 2. And then we're going to get that. Okay, so then we have this. So then I will, is it S over 2? Yeah, it is S over 2. Yeah. So, okay, so then we have I naught is equal to 1 over S plus 2. Or actually, I'll be 2S squared. And then we want to factor this. Well, okay, I'll just write it normally first, and then we want to factor it because we want to have to just do a partial fractions, obviously. Most of these things are partial fractions. So there we go. Those twos cancel. Is it okay if I use a partial fractions calculator, or do people want to see the actual full partial fractions process here? It's really up to you guys. Like sub in IO during your nodal, essentially. If I subbed in my IO during my nodal here, if I did that, so then I essentially just say this is IO here. Is that what you're saying? Like just directly, just say this is IO. I'm gonna take, yeah, right? Well then how would I rearrange it? Because then I'd have IO in terms of V, right? And then I still don't know what V is though, right? So I would have to do it like this, right? What happened to 2 in the, okay, you got it. So that's okay. Yeah, I've canceled that. Okay, someone asked for me to do the partial fraction, so let's do the partial fractions and let's see how it goes. So S squared over S plus 2, okay. So we want to factor this, so I want two numbers. This is how I always write it. That add to 1 and multiply to 2. Well, so I don't think that has real roots. There's no two numbers that add to 1 and multiply to 2. No, I think that's everything. Yes. Yeah, there's no real roots. So we got to do this the full way. So that essentially I'm not going to write anything different here. Yeah. So partial fractions now. Partial fractions is going to be, well, our thing is S. I'll just copy and paste it so that I don't have to write it all again. And then B, put that there. What I'm going to do is I'm going to set this equal to A over S plus 2, right? Plus BS plus C over S squared plus S plus 2, right? So that's how I'm going to break this up, because I know I use my two factors. Like the linear factor gets a 0th degree one, quadratic factor gets a linear factor. And then from here we can say, okay, so multiply both sides by the denominator. So S squared is equal to A times S squared plus S plus 2 plus, okay, now that's going to be BS plus C times S plus 2. Okay, so if there's any confusion, let me know. We can work from there. Otherwise, this is this is AS squared plus AS plus 2A plus BS squared plus 2BS plus CS plus 2C. So hopefully, everybody's following so far. So I'm just going to group together all the S squared terms, right? So all the S squared terms is just A plus B, that's it, right? All the S terms come together, so it's just A plus 2B plus C, I think. A plus 2B plus C. That's everything. Let's just check. Yep, that looks good. And then all the constant terms come together. So it's just going to be 2A and then plus 2C. That's all. And then we can conclude from this that A plus B equals 1, A plus 2B plus C equals 0, and 2A plus 2C equals 0. Then you can solve this however you want to solve it. Doesn't really matter. We can solve it by substitution. Why what? Yeah, why? How did I make the system? Is it the question? How are they, like, why did I make these equals? Yeah, okay. So the idea is that from this line right here, I'm looking, the left side is a polynomial, right? The left side, I could think of the left side as, 1s squared plus 0s plus 0, right? 0s plus 0. So if these two polynomials are truly equal, then their coefficients must be equal. A plus b must be equal to 1, because that's the coefficient on s squared. And then, I shouldn't use that color, should I? Right, then 0 and a plus 2b plus c should be equal, because that's the coefficient on the s term. And then the constant, can't use that color either, can I? The constant term, need better colors. Let's see. That's a good purple. The constant term and the constant term should be equal if these are truly equal polynomials here. And that's the idea. You make a system and then you use that system to solve for the variables. So you're essentially matching the coefficients. The coefficient of s squared, the coefficient from s squared matches the coefficient on s squared on the other one. Coefficient on s matches coefficient here. Constant term matches the constant term. So hopefully that makes sense. If not, let me know. We can keep talking about it, but I think it should be good. So then from here we can solve this. However, I'm tempted to use a matrix, but we can just substitute stuff in. Like we don't have to do that. So this is just a is equal to b 1 minus b, right? And then I can say that let's see, how's it going to be here? Here I can just substitute in here. C is equal to negative 2b minus a. And then here actually I'll rearrange this to be a. Yeah, I got it now. A equals 1 minus b. There we go. A equals 1 minus b. C equals no, sorry, I think I had the right way before. So I'm gonna replace b with something to do with a. Yeah, I had it right before. B equals 1 minus a. Okay, the reason I'm saying this is because of course you can do this with a matrix and you can do this with a calculator, but I'm just trying to do it by substitution. So what I'm doing is I'm just going to take this last equation. I want it to only have the variable a in it, right? So I can substitute these into each other. So it's going to be c equals negative 2 1 minus a, right? So now c is just in terms of a, and then I can substitute that into this equation. It's going to be 2a plus 2 times negative 2 1 minus a equals 0, and that's just an equation with a in it, right? So we can do it like that. Of course, there is other ways to solve this, but that's probably the most straightforward way. So plus 2 times negative 2 plus 2a minus a equals 0. 2a minus 4 plus 4a minus 2a equals 0. So 4a equals 4, a equals 1. So there we go. There's that. And then now that I know a equals 1, I know b equals 1 minus a, b equals 1 minus 1, b equals 0. Right? And then c isn't also entirely in terms of a, so c equals, what did I say up here? Negative 2, 1 minus a, negative 2, 1 minus 1 minus 1. So negative 2 times 0 minus 1, negative 1. You could do when s equals 2, which gives you a equals, and then check the coefficients to get b and c. Yeah, so you could also do that method where you say, like, okay, set s to be, what was the factor? Yeah, negative 2, and then you lose the term, and then it goes away. Yeah, but then I wasn't going to do that just because there's nothing you can plug in for this one, right? So we can't really do that well with that one. But anyways, there's our coefficients. So we figured out c is all of these, a, b, and c. So now I can finally go back up to my start of the partial fractions. So we go here. Oops. And I will plug everything in. So a is 1, b is 0, c is negative 1. So this means this is 1 over s plus 2 plus negative 1. So I'll just say minus 1 over s squared plus s plus 2. S squared plus s plus 2. So finally, we're not done yet, but that is our I0, right? And it is in a form now that's a lot easier to take the Laplace inverse of, right? So that is our Laplace inverse of, I0 of s. So then I0 of t is going to be the Laplace inverse of this. Now, before we do that, actually, I'm going to have to get the denominator into a form that's nice too. So I'm going to do, I'm going to complete the square, right? Complete the square on it. So here, this is how I do it. S squared plus s plus 2. So it's a 1 here. 1 divide by 2. This is how I always draw it. So you take the 1 over 2, and then you square it. And so that's a 1 over 4 there. So then I also want to obviously subtract 1 over 4, right, plus 2. And so then this is going to be s squared, s plus a half squared minus a quarter plus 2, and s plus a half squared. And this is 8 over 4. So this is plus 7 over 4. So I completed the square then. If there's any questions about that, let me know. I know I did that fast, but it's just because it's just completing the square. But if anyone has trouble with it, don't worry. We can go through it. But that would be the completed of the square there. Okay, sounds good. So then I can turn this into 1 over s plus 2 minus 1 over s plus a half squared plus 7 over 4. Okay. And so let's just take this bit by bit here. So the first inverse Laplace would be the inverse Laplace of 1 over s minus a, right? So this is really 1 over s minus negative 2 minus this whole stuff, s plus a half squared plus 7 over 4, right? So if I just start breaking this up now a little bit into the time domain, right, this would just be e to the negative 2t for that first term. And in the second term, we got to look at some sort of formula that's going to help us with this, right? So it's going to be it's going to be sine or cosine or something like that. Let's take a look. So yeah, it looks like it's going to be sine. So let me just do that quickly here, right? So that is a formula that we have, right? 1 over s squared plus k squared. So that's essentially what we have, right? So I can just rewrite that term right there. So I'm going to note here. So note that 1 over s plus a half squared plus 7 over 4, right, is equal to, and so if you look at this formula, you have a k on the top and a k on the bottom. So this is something squared. So I got to write this as, root 7 over 4 squared, right? But I also want to have a root 7 over 4 on the top. So it's going to be root 7 over 4, right, over s plus a half squared plus root 7 over 4 squared. And I just got to multiply by 1 over root 7 over 4. So let me make that a little unsquished there, but hopefully that makes sense. So I just want to have the k on the top, k on the bottom. So now that I have this, it's in a much better state to take my Laplace inverse of, but it also has this s plus a half there, right? So that's going to make things a little bit more complicated, right? But I think we have, we also actually have a nice formula for it. Let me just make sure it's here, s minus a for k. Yeah, there we go. So of course you can use the translation theorems, or you can just match it from a table. So from this table, we can see that if I have k over s minus a squared plus k squared, right, then it's just going to be this. So that means that that term is going to be e, what's our a? A is negative a half, so e to the negative 1/2 t sine of root 7 over 4 t. And there we go. That should be it. That's our answer. A0. There's no Slater solution, so I can't really tell if that's right. But hopefully, if anyone's doing it with me, then they can take a look.
I just got a question
Yeah.
about when we are like early on when we were making our equation and then you subbed in I naught into it because we knew what I naught was equal to.
Yeah.
Yeah, so a bit
Which is
higher.
up here, somewhere here. Yeah.
Yeah, so it was right there, that line. So what exactly happened to the from the top equate exactly that one to the
Like
next
from
one?
here to here, essentially. From here to here.
Exactly. Yeah.
Well, I just noted that the thing we're looking for is equal to V, right, times V times S over 2. So V is the expression we just got over here. So then I'm going to just multiply that expression that I just got by S over 2. And so now I'm going to get I. Essentially, I'm substituting this into this equation.
Yeah.
That's what I'm doing.
Okay.
I'm substituting
yeah,
that.
yeah, exactly.
It's probably a better way of thinking about it. Yeah.
Yeah, yeah. Thank
So
you.
I'm taking this, substituting in there. Yeah. Someone's gonna say something. I think someone's saying I made a mistake.
Yeah. Okay.
Yeah,
It's just a 1 over root 7 over 4.
Oh, I just
in the
forgot to
end.
include that? Yeah, I just
Yep.
forgot to include the 1 over root 7 over 4. Yeah.
Yeah, it should be root 4 over 7.
Yeah. I'll write it as 1 over root 7 over 4, but yes.
Okay.
Of course, that is correct what you're saying. Yeah. And then you can simplify that a little bit more. Yes, that's true. So I will do that, yeah.
Also,
mhm.
don't we technically need to multiply everything by U of t because
Yeah.
that's how they want to be?
Yeah, for sure. I see that people are saying that too. Yeah. That's the end of the Laplace, and then we will add that at the end here for sure. So the final answer for the actual question is essentially you just add the unit step function to everything, right? So you just multiply everything by U of t, and the reason for that is because we don't really care about like this. That is true for the circuit after t equals 0, right? That's when the circuit starts acting like this. We just don't know what's happening to the circuit before, right? We don't know. Like, there's no reason to use that for before t equals 0 because that source is not there. The function exists before that, but we don't want to be allowed to use that, so we do it like that. And there you go. That is that should be the final answer for that question. So, any questions about that? And then there were some questions in the chat, so let me take a look. Let me take a look at what are the questions. So is the table from the ELE textbook? I'm using my table from the math textbook, and it's actually my math textbook, not like mine, but there's the textbook Advanced Engineering Mathematics 6th edition. If anyone wants the textbook, just message me after, and I can help you find it. But yeah, essentially it's just has a good table. Maybe I'll post the table in some chat in the Discord chat after or something like that. I can't post it right here, so it's just a good table. I don't like the ELE tables because they're just not great. Okay, good. So people are telling me they match my solution, so that's very good to hear. Someone said, can you quickly explain again why you didn't include the current source in S domain? I believe it has something to do with initial conditions. Yeah, so when I went to Laplace domain, I did include this current source, right? But I didn't include any other extra sources on these guys. And that's because those current sources entirely depend on the initial conditions of the circuit. But the initial conditions of the circuit were 0. So 0 over S is 0. So they may as well just not be there. Right? It's a parallel line with 0 amps going through it. It just may as well not be there. And same with this here. The initial conditions are 0. Could we have found the inverse Laplace without completing the square? If you have a really good table. But I don't think any table would have that. I think you have to complete the square. Yes, I forgot to multiply by 2 over root 7, but we got that. Add that. When drawing the circuit, why does the current source disappear? Which current source? Hashem. Which current source disappears? This current source doesn't disappear.
No, yeah. Ignore what I asked.
Okay,
I figured it out. Yeah.
Okay. Okay. That's good.
I have a question.
Yes.
You know where you converted from time to Laplace for the circuit
Yes.
about it's all the way at the top.
Yeah.
Unlucky. Why did you only do it for the inductor and not the capacitor?
I did it for the capacitor here. Capacitor here too.
No, but keep scrolling up.
Up? Sorry, up
Up,
here?
yeah, up. Yeah, that one.
Oh,
that,
why
right
did
there,
I
right
only
there.
show the picture?
Yep.
Yeah, I only showed the picture for one. I should just show the picture for both.
It's just both of them are 0, so it doesn't matter.
Yeah, the other one will also have another source, which depends only on the initial condition, and it's 0.
Okay,
so
makes sense. Thank you.
You can find it in my notes too if you want the pictures. Okay, I'm happy we made it through that. No problems there. Good. Okay, so let's finish up. I guess I will clean this up just a little bit. So 1 over root 7 over 4 is root 4 over 7, which is 2 over root 7. So I'll just add that there. And then there we go. That should be our final answer. Good. Let's move on. We want to, keep up with time here. Let's move on to magnetically coupled circuits. Of course, if anyone has any questions, feel free to ask. But let's do the magnetically coupled circuit next. We'll do the whole thing. I was going to say, we don't have to actually solve the whole thing, but just in case people want to see. So this one is going to be from a previous exam. And this is pretty interesting. I do like this stuff. I mean, I like ELE, but this stuff especially. So the magnetically coupled circuit one, essentially all it is we just want to find the two mesh currents. I think that's the whole question. Find the mesh current, find the other mesh current. Yep, just find the two mesh currents. Okay, that's a simple one. But of course we have magnetically coupled inductors here. So let's do our loops. So that is the loop for I1, and that is a loop for I2. So let's make both of our equations. So the I1 equation is going to look like this. So going into the negative terminal, it's going to be negative 100 to an angle 0 plus 10 I1 through there. Okay. And then you just treat it as the impedance. So we can ignore the dots for the moment, right? And I'll explain how the magnetically coupled stuff appears in a second. But, just for now, it's just an impedance there. So J10 I1 plus J10 I1 minus I2, right? And if there was no like a mutual inductance here, we could just end there. We could say E equals to 0. But we have an extra term, and that's because these two inductors are magnetically coupled. And that's because we see this little drawing here, and we have the dots that help us out. So the current going through this inductor is going to induce some sort of charge on this inductor. That's the idea. The current going through here is going to induce some sort of charge on here. So voltage difference, I mean, right? It's induce some sort of voltage difference. So first of all, we got to decide if it's positive or negative. So the way you do that is you look at the current that's creating the voltage difference, right? And you ask, is that current going into the dot, right? If it is, then the dot is the positive one on the other one. If it's not, then it's not. So here, right, the current is not going into the dot. The dot's over there, right? But at least, I mean, if it was over here, then we'd still say it's going into the dot, right? It matters top or bottom. So it's not going into the dot, which means this is the negative side of the mutual voltage that's created. Okay, so we have an extra little voltage that's happening there, little thing. And so it is going to be minus J5, because of that, J5 right there, created by I2. Right? Yeah, I can repeat it for sure. So that's going to be our equation for I1 there. So let me recap that. Well, how about I'll make the other equation. It's going to be the exact same process with the other equation, and then I'll recap after I do that. So I'll just make the second equation first. So for I2, very, very similar process. Right? I'm going to erase these dots. Now we don't really care about that anymore. Okay, for I2 isn't the only current in the vertical inductor. Yeah. Oh, you're right. That current isn't going through there. Yes, you're right. I see. Yes, thank you, Hannah. That is true. So this current, you're right. This current is inducing that thing right there. But a slight mistake I made is that's not just I2, is it? Right? That is I2 minus I1, right? Because I2 is going in the same direction, I1 is going in the opposite direction. So it's actually going to be I2 minus I1 there, right? That's equal to 0. Thank you, Hannah. That is true. So again, just repeating the thing that just happened there is that this current going up, right, is inducing that charge, right? But that current is going to be some combination of I1 and I2, right? That combination of I1 and I2. Okay, now let's do the other one. So if that inductor was like where the capacitor is, then it would just be I2. Yeah, then it would just be I2. Yeah. Yes, because there's no two things happening there. Yeah. And that was like a resistor or something? Yeah. Okay. Wait, doesn't the right inductor also? Yeah. The right inductor has mutual inductance on the top left. Yeah. The horizontal inductor also induces a voltage on the vertical one. Yeah, and I'm going to do that in my I2 equation here. Oh, yes, I'm going to do that in here because this is going to be another one here. Yes, that's true. Okay. Thank you guys. So I will highlight everything after to make sure that we get everything right. Very good. I'm going to highlight what's the mutual stuff. So this is the mutual, right? This is the mutual stuff. We're going to have an extra mutual term here. I'll explain that in a second here, right? Equals 0. And here, right? This is all our normal, totally normal KVL stuff that we're creating here. So that is just KVL. And then the complication is that, so I'll just highlight that here as KVL. And then the complication is that we have some mutual inductance, mutual voltages happening. So the first one is an additional voltage created on this one, but there's also an additional voltage created on this one, right? This inductor gets an additional voltage because of this inductor. So the current going through this is inducing some sort of charge, some sort of voltage difference onto this. So we determine the sign, first of all, by saying if the current is going into the dot on this one, on the one that's inducing it, the dot is the positive side here. So it is going into the dot, the current's going into the dot, so that's positive, negative. And so in this loop, it's going to be plus, it's going to be J5, and what's inducing this current? That time is just a I1, right? I1 is just the thing inducing that current. Okay, any questions? I think someone...
Yeah, when you say going into the dot, do you mean the dots are on the same side of the inductor?
I mean that like this current that is inducing that charge on this inductor, the direction of that current is into the dot. It's not this way, right?
Oh, okay.
It's not like
okay,
that.
yeah. So basically okay, I see. So the same current is going through the dot here and it's going through the dot here.
Yeah, the same. So if this current is going into the dot, then this is the positive. That's the positive side. The dot on the other one is the positive one.
Okay.
And otherwise, it's not. That's all it is. So I1 or I1 minus I2. Well, the thing creating this voltage difference is I1. So it's just going to be I1 on that one. Right. That's all it's going to be. Okay, good. That should be good now. So there's our mutual inductance. Oops. Or mutual, I don't know what to call it. Mutual inductance, I guess. Right, we get that. So then our next one, the next equation is going to be very similar. Right? So I'll ignore the mutual stuff for 1 second, and then here it's gonna be a simpler one. So it's gonna be just 10I2 minus J10I2. Okay, I'll subtract that. Okay, then we have plus J10I2 minus I1. Okay, and now we just have to count. So that's our regular KVL. Sorry, I'm getting vibrations. That's our regular KVL around that loop. And then now I want to do the mutual stuff. I want to do my mutual inductance. So the mutual stuff is going to be simpler this time because there's only one inductor in there. So there's only one extra voltage that's happening. Here there were two inductors in this loop. So there was two extra voltages. But here we just have one. So then I ask myself again, right? So this current is going in, well, let me be more clear. This inductor, the current through that inductor, is inducing some potential difference across this inductor. That inductor is in this loop, so we have to account for it. So, first of all, polarity, determine the sign, right? Is that current going into the dot on this one? It is. If so, then this is the positive side. The dot is the positive side on the other one. Okay. And then from here, right, we just account for this. It could be minus J10, and what's creating this extra voltage, mutual inductance, is I1. It's just I1 creating it. And there's our final one.
It's J5, right? Not J10.
It's J5.
Yeah.
From there. Thank you. Isn't it? Let's see. Okay, so a bunch of questions. So let's see. Isn't it negative J10 because the current is entering through the negative side in terms of KVL? Negative J10 for which one? For this one? For I2? This here? I have negative J10 here for this one. No, that's for the capacitor. For I2, which term are you talking about?
Oh, I think he means because there's we know like there's a potential difference across the inductor that goes positive to negative, but like it's going opposite of the direction of the current. Like we're going minus to plus. But they're actually like we're doing what's it called, like superposition. Like we're assuming that there's a voltage drop across the inductor going in the same direction as I2, but then there's an induced voltage that's in the other direction that's caused from I1.
Yeah, so this is the one that's in the same direction, right? And then this is the one that's caused by I1 here. Right? Yeah. Exactly. So just, yeah, what's going on with this inductor? Okay,
Wait,
so
wait,
there's lots of questions. Yeah, go ahead.
I just have one question. So on the first thing that we wrote, right? So the J5 I1 minus I2, like the mutual inductance, the first term is the inductance on the which one is it? Like what is it induced by? Which inductor is it induced by?
Yeah, okay, so this is induced by, so induced by, I'll just label this one 1 and 2. So this is induced by 2 on 1. This is induced by 1 on 2.
Okay, thank you.
Make sense? Okay. And does that make sense why?
Yeah, I know why, but I was
Okay.
just confused. Just got
Yeah,
confused. Right?
Yeah,
Thank you.
yeah. Good. Okay. Okay. So why? Okay. So someone asked in the chat why. So the reason is because the current we sorry, the current we use in the term is always the thing doing the inducing, right? That is the inductor doing the inducing. So what inductor has that current going through it? Current 2. As inductor 2 has that current going through it, right? And what inductor has current I1 going through it? Inductor 1. Why is it negative? So yeah, that's going to be the sign thing. So yeah, so let's go through the signs again. I'll go through. I'll just talk through. Let's start from the beginning. I'll just talk through deriving these things again, right? And I know there's lots of questions about it, so we'll make sure we get through everyone's. So again, this is going to be your loop 1, I1. This is going to be your loop I2. So honestly, let's start with I2. I2 is kind of a simpler one, and then we'll do I1 after. So let's start with I2 here. The KVL should be pretty straightforward. So it's just 10 I2. I start with that source minus J10 I2, okay, and then plus J10, and then just you have to ask yourself, what's this current? So the current is I2 minus I1 going through there. But that's going to come up again, right? That current going up like that is I2 minus I1. But let's leave it like that for now. Then you have to say, okay, well, these inductors are magnetically coupled, right? Which means they're interacting with each other because of this, right, to add an extra voltage onto each other. So there's an extra voltage being put onto this one, superposition on top of it, right? But you can just account for it with another term here. And it's going to be, again, we're looking at I2 first, right? We're looking at that's the one we're looking at first here, right? So I'm going to try to make this term. So it's going to be this, right? This impedance times the current which is creating that impedance, creating that voltage difference. This inductor is creating that voltage difference. Okay, so it's this current which is creating an extra. Well, I don't know if it's positive there yet, but it's creating some sort of voltage difference across this inductor, and so I'm going to write that as this impedance times that current. Okay, so it's definitely going to be J5 times I1, but then the sign we have to ask ourselves. Now, this is just the best way of going about doing it is saying, look at this current here, this current that's causing the mutual inductance. Is it going into the dot? Yes, it is going into the dot. Therefore, on this inductor, the dot is the positive one. If the dot was over here, let's ignore that for a second. If the dot was over there, current was coming in here, it's not going into the dot anymore, so the dot is the negative one. Hopefully that makes sense. So the dot is there, current's going into the dot, that's the positive side. So now when I do my I2 loop, if you look at this I2 loop, the current's going this way, right? So it's negative relative to that. So it's going to be minus J5 I1. Minus, because that's the minus side, and we're going up like that, right? With our loop. So any confusion? Of course, unmute or message if you have a confusion. And then for this first equation now, there's no confusion. For this first equation, there's two terms added. So let me erase all this stuff, right? So we can just essentially forget about all this, right? There's two terms added. So first of all, okay, it might help to draw the actual induced voltage sources. So like drawing the actual, you're saying like draw like a little on top of it, like a little thing like this, which is another J10. Yeah, I guess I could do that. So it's going to be like, there's going to be, for this one here, there's going to be an additional minus, well, there's going to be additional J5I1 created right there, right? J5I1. How did I get that? J5, what's inducing it? I1. J5I1. And then it's going to be that polarity because of the dot convention. And then you have that there. And so that's what's going to contribute to that right there. Okay, so then let's try the other loop. The other loop is going to be very similar. So, I mean, the KVL part is pretty simple. It's just, okay, so going in here, it's negative 100 to angle 0, 10I1, J10I1, J10I1 minus I2, right? And that's everything. And now we have to account for the induced voltages. Okay, so we did the normal KVL. Now, this inductor is inducing a voltage on this inductor. This inductor is inducing a voltage on this inductor. So we need to account for both of them because both of those inductors are in this loop here. So first of all, let's figure out this inductor is inducing some voltage on this one, right? So it's going to be written, let's figure out the sign first, figure out the sign of that. So we got to figure out this inductor here, what's the current going through it? So I'll just match the direction like this. So the current is going like that, right? The value of that is I2 minus I1, right? Very importantly, it's not just I2, but it's I2 minus I1. That's the current going up like that. That current is inducing a voltage onto this inductor. So now the polarity is going to be, we take a look at this arrow. Is it going into the dot? It's not. So since it's not going into the dot on this other one is the negative side. Can we also say the current is going down, I1 minus I2, but it's going down? Yes, you can do that. Yes, and then the polarity will change on the inductor too. Yeah, so this is the same as adding a current-controlled voltage source element, right? A current-controlled voltage. Yeah, I guess it is. Yes, current-controlled voltage source circuit element. Yeah, that makes sense to me. So there we go. That's how I make this term here. So it's going to be a negative one going in there. So it's negative, first of all, because we're going into the negative side. The impedance is J5, right? And the current causing this is I2 minus I1, right? So that's what I include in my equation right here. My equation right there, right? Obviously, it's getting a little messy, but hopefully you can still read it. So that's the negative side, that's positive side. It's J5, I2 minus I1. So we're going in the negative terminal, so it's going to be negative J5, I2 minus I1. So you see, this is the voltage induced by number 2, the second one, onto the first inductor. Okay. So, if there's any questions, let me know. Happy to help. Okay. And then this other one here, we got to account for the next voltage. I'm just going to erase this just so we have a little bit cleaner slate here. This inductor is inducing a voltage on this inductor. Okay. So polarity, current going through this guy, is going into the dot. That means the dot on this one is positive. That's the negative one. Now, so we're going to have a positive additional voltage here. And it's just going to be J5 times the current that's causing it. I1 is the current that's causing it. So we get that. J5 plus J5I1. And then there's that. There we go. And the sign is because current's going into the dot is positive. That's an important thing. Current going into the dot is positive on the other one. Okay, I will stop for a second if anyone has any questions. I know lots of people had questions before, but hopefully me repeating it through there helped. I missed a few messages there, but if I miss your messages, tell me again, and then I'll take a look. For the KVL part, are we using passive sign convention so the dot doesn't matter for only that part? For the KVL, so just the KVL part, yeah, the dot doesn't matter for just, yeah, the dot doesn't affect this part. You're right, the dot doesn't affect this part. The dot affects the mutual induced voltage. That's correct. Someone asked, why is the second one negative J5 I1? So let's see, negative J5 I1, this one here, that's what you're asking? Yeah, probably, negative J5 I1. Yeah, so that one comes from our I2 circuit, so let's go through that, right? Our I2 loop. So what's happening is, so we've accounted for this, this, and this already in the pink section there. Now this inductor is inducing a voltage across here, across this inductor. Let's check the polarity first. The current of this inductor is going into the dot, so the dot is the positive side, right? And now, so that means that, you know, relative to our KVL, which is going that way, right? That's just going to be a negative, right? It's going to be a negative J5 times the current that's causing the voltage, which is I1. I1 is causing the voltage. J5 I1, and you're going to make it negative. Does that make sense? Okay, sounds good. Perfect. Okay, so if there's any more questions, let me know, but I will start, you know, trying to, I mean, basically from here, you just want to solve for I1 and I2, right? We have a system of two equations, two unknowns. So we'll go ahead and do that. I do it in like kind of a particular way. I don't know. I'll just show you how I do it, and then hopefully, I mean, of course, there's lots of ways to rearrange these equations. I won't do any kind of matrix stuff, and I could technically, but I won't. I'll just do a substitution. But how I like to do is I like to just make a bracket for I1. So all the I1 stuff goes in here. So 10 plus J10, okay, plus J10 again, plus J5 plus J5. Okay, and then I'm going to make a bracket for my I2 stuff, right? And it's going to be minus J10I2, sorry, J10I2. Okay, minus J5I2. That's it, equals 0. Oh, sorry, equals 100. So I just essentially grouped together all the I1. I distributed this in, and then grouped together all the I1 stuff and all the I2 stuff. Someone could just verify that, because, you know, I don't want to make a mistake here. I'd appreciate if someone could verify, but I will verify if no one else does. And then the I2 stuff that I'm going to put, sorry, I1 stuff for the next line is going to be negative, well, why am I starting on that side? I1 on this side is going to be negative J10, negative J10. Oh, sorry, there's no need for I2s in there. It's there. Okay. Negative J10. That makes sense. Minus J5. That's all that I have for I1. So now for I2, it's going to be a little bit longer. 10 minus J10 plus J10. And that's it. Equals 0. You're good so far? Okay. Sounds good. Thank you, Hannah. So now I'm going to just substitute one equation into the other, really. So I will rearrange, well, sorry, I'll simplify a little bit, and then I will do that. So this is going to be 10 plus J30 plus I2 times negative J15 equals 100. I1 negative 15 negative J15 plus I2 10, just 10 equals 0. So I'll rearrange for I2 here. So I2 is going to be I'll call it this, J15 I1 over 10. That should work, I think. J15 I1 over 10. Yeah, that looks right to me. And then I'm going to substitute that into this equation. But let me just show. So those are the two equations together. Those are the two equations together. And I'm going to take this equation, turn it into that. And now I'm going to substitute this equation into there. So it's going to be I1 10 plus J30 plus, now I2 is J15, so I'll say 15 over 10 JI1. I think J5 will always be given. The mutual, like, I don't know what you call that. The impedance, mutual impedance. I don't know. I think that'll always be given. How did I get the second equations? Where did I get this? Where did I get this I2 equation? Yeah, I just rearranged. I rearranged this. So I rearranged this into. Just give it a try. Just rearrange this into I2, and you get that for I2. So I rearrange that. Hopefully that makes sense. How do I get the second equations? Do you mean this or do you mean this? The second equation is from the two groups. So I'm going to assume you mean this right here, right? From the two groups. Yeah. Okay. So how did I get those from? Sorry, how did I get the second ones? Well, essentially all I did is I just simplified what's in the brackets here, right? That bracket simplified into that. That bracket simplified into that. That bracket simplified into that. And that bracket simplified into that. Does that make sense? Do you want me to explain any of those? I can if you like. But... Make sense? Okay. I can't tell. Does that mean yeah, explain it? Or does that mean no, it's okay. I can keep going. Okay, sounds good. So then we can continue here. I2 is 15 over 10 JI1, but I'm getting really crooked here, so let me fix that. JI1 times 10 equals 0. So then this is just I1 10 plus J30 plus 15 JI1 equals 0. Isn't it x minus J15? Yeah, where should it be x minus J15? Well, probably not x, but it shouldn't be times 10 times negative J15.
I mean, where did the 10 go? Isn't it 15 over 10?
Oh, yeah, you're right. I was looking at the wrong one there. Yeah, for sure. Okay, I see the issue. Thank you guys. Yeah. So I'm substituting into this equation. So that's going to be J15 over 10 I1 times negative J15. Yes. Equals 0. Yes. Thank you for that. That is correct. So from here, I could tell something goes wrong because no, it's okay. It's okay. I understood. Yeah. I could tell something goes wrong because we were going to get a bad result. So that's fine. So here, if I just substitute in, yes, it should be 100 on the right. There we go. That is the issue. It should be 100 on the right. Perfect. Obviously, I'd usually do this with Kramer's rule. So there we go. We get 10 plus J30, and it's going to be minus 15 squared, whatever. Minus 15 squared over 10 J, like that. Seems right to me. That looks good. The minus goes there, and the J, and then everything goes there, equals 100. So then we're going to get I1 equals 100 over all that. Just rearrange that there. I got a little bit of luxury. Yes, you are right. There's a J squared there. That is J squared. Yep. 15 squared over 10, J squared. Yeah, you're right. So the J's also multiply. I don't know what's going on. So then this simplifies into, how is I2 I1 times J15 over 10? From this equation here. This equation here, I rearranged that. Right, move it over. It's going to become positive. J15 I1 divided by 10? Yeah, okay, you're good. Okay. So this will then simplify into something a little bit nicer then. So it's 10 plus J30, and this is going to be plus 15 squared over 10, right? Because the J squared is negative 1, so then you just have that. Okay, and then we will have our first solution, which is, well, it's essentially that's the answer, but I'll just type it into my calculator and see what my calculator gives me. 100 over 10 plus 15 squared over 10 plus 30i is 1.6613 minus 1.5 3, 3, 5, J. And then we'll just put that, I mean, I'll just leave it in rectangular for a second. I'll put in polar at the end. And then I just want to use this equation right here. Okay, use this equation right here to figure out I2. So I2 is equal to J15 times 1.6613 minus 1.5335 J, oops, over 10, which gives me, I'll just say answer times 15I over 10. Yep. And that gives me 2.3 plus 2.5 J. And then I'll just convert both of those to polar form, and then that'll be our final solution. What happened to the J squared before you plugged in calculator for I1? I plugged this into the calculator. That's what I plugged into. So the J squared became -1 and just turned that positive. That sign, that term right there, positive, because -1 times negative. Make sense? Okay, sounds good. So I'll just quickly get the magnitude of everything. So I can get the magnitude of the last one pretty easily. So I2 is going to be 3.4 to an angle, and I'll just find the angle, tan inverse of 2.5 over 2.3 to an angle 47.4. And then I1 is going to be negative x, so tan inverse of negative 1.53. Well, so let me show you how I'm going to get the angle for this one, because sometimes the angle stuff is kind of complicated. Well, not really complicated, but confusing. So let me get the magnitude quickly. 1.6613 minus 1.55. Just going to get the magnitudes. Okay, so the magnitude is 2.26, and now the angle for this one we'll look at together here, right? So to find the angle, let's say for angle of for the angle of this, well, we want to draw it first, right? So the x component's positive, the y component's negative, right? Okay, so actually then just typing in tan inverse is going to give you the right answer. Yeah, I thought that was more complicated for a second. No, just tan inverse of it is going to give you exactly the right thing. Negative 1.5335 over 1.6613 gives me negative 42. So negative 42.7 degrees, and there you go, negative 42.7 degrees, and that's fine. So there was no point of even mentioning that. There we go. That is our final answer for the two mesh currents. So really the complicated part is making the equations, and then after it's just kind of tedious, prone to mistakes.
Don't we have to convert the final thing to time domain? Or no?
We weren't given it in time domain. We were given it in phasor domain. So
Oh, okay, okay.
we don't know the frequencies, so we can't do that yet. Okay. So hopefully everybody is okay with this. If there's any questions, let me know. Otherwise, I will move on to the three-phase circuit. Okay, sounds like we're good. Oh, someone said, why is J5? Why is J5 I1 minus I2 negative? Where is J5 I1 minus I2? J5 I1 minus I2 right here. Okay, so first equation, yeah. So that is going to be from our I1 equation, right? What that is it's the voltage that's induced by this one onto this one. Okay, so the current here is going up through. I'm just doing that to match this, right? So it's going up through. That current is going not into the dot, right? So if it's not going into the dot, then this is going to be negative here, right? Then the dot on this one is negative. If it's going into the dot, then this is positive, but it's not going into the dot, so it's negative. Okay, good. Tan inverse negative 1.5 over 1.6. Yeah. Yeah. Sorry, could you show I1 again? Yeah, the I1 equation, you mean?
Yeah, the I1 equation.
I1 equation. Yeah, no problem. So are you okay with all the KVL stuff?
Yeah.
Okay, so then the mutual stuff. So the mutual stuff, I just explained this first one. Do you want me to explain this one again? I can, don't worry, but
No, oh no, not this. I meant like the final, because I'm getting a number on my calculator, which I'm not sure how to
oh,
read
I
on
see.
this
Okay,
OT.
how you got the
Yeah.
I1? Well, did you get this?
I mean, it might add up to that. It has two complex numbers stacked on top of each other.
Two complex numbers, like it's division, like as the
Is
fraction?
it? I'm not sure. There's no extra division sign between the two complex numbers. It's just
So your
like
calculator
negative,
is giving you two complex numbers as the answer?
yes, on top of each other. So it's like negative 200 divided by like 129. Then under that is negative 480 divided by 169i.
Oh, so it's giving you something like whatever, something like this, a over bi, like this,
Yes.
like that. All that is it can't write it on top of each other. This is the number, negative 200 over 129 minus a over bi. That's the number. It's just that sometimes the calculator runs out of visual space for whatever reason, and it just decides to write things stacked on top of each other. Right? That's all. That's all it's gonna be. So, well, let's check. Yeah.
Wait, how did you convert it to like polar form though? Did you just use your calculator?
Yeah, I just use my calculator.
Because I'm getting something different. Can I see?
Yeah. For which one? For I1?
For I2, I get like a bigger angle. I get 132.7. I have the same 3.39 though, but the angle is different.
Okay, and you have 2.3 plus 2.5 I. That's what you got for that's the card, like
Yeah,
the
that's what I
rectangular one?
inputted. Yeah.
Let's try tan inverse of 2.5 over 2.3. I get 47.4. Yeah, I'm getting 47.4 here. So you're typing in tan inverse of 2.5 over 2.3?
Okay, I think I got it now. I think I have to use the function. Okay, thank you. Sorry
You
about that.
okay? Yeah, no problem.
Yeah.
No problem. Of course. Okay, great. So let's move on to three-phase circuits. Of course, if anyone has any questions, but I want to keep up. We only got 40 minutes left, so I want to get everything done. So three-phase circuits. Three-phase circuits are actually not that complicated. I learned them pretty I learned them pretty quickly with a nice group. So we did some good work, and it actually they're not that crazy. So essentially, the main thing is like converting between all the different forms, right? That's almost pretty much the main complication here. So let's just look at this. So this is a three-phase circuit. This is the source, obviously, in delta configuration, and this is in Y configuration, right? And notice here that the impedance, right? The impedance of each line here is ZT and ZL, right? That's the impedance of each line. So the first thing we want to take a look at is compute the line current through ZT. Okay. And when they say the line current, which is something that confused me a lot when I was doing these things, is when they say the line current, I'm fairly certain they mean the magnitude of the line currents, the multiple line currents, because these are all the line currents, right, going out like that. And there's three of them. There's not just, compute, like, well, I guess they meant to say the line current. But I think they mean the magnitude of the line current. They all have the same magnitude. So we're looking for this current here. There's a they all have the same magnitude. They're out of phase with each other. That's the point of the three-phase circuit, is that they're all out of phase with each other. But there is the same magnitude going on there. Okay, so I did some of this before, so I'm gonna make sure that I copy that so that I don't make any mistakes. First things first, we want to tell if this is a positive or a negative sequence, like Ethan just said. The phase of each current would match the phase of the voltage source. Not necessarily. I don't think it matches exactly the phase of the voltage source, but they're out of phase by just as much. We'll see. We're going to calculate it, and we'll see if I understand. But they're going to be out of phase with each other by just as much. Yeah. Sorry. Okay, so now we will we'll start to do this. Compute the line current through ZT. The line current is the current that goes through, well, it goes through here, right? But let's try to understand what the loop is, the loop that it's going through, right? So it definitely goes through here, it goes through here, and then what happens here is essentially the question. Like, what's going on here, right? Well, what you can think of is that there's a neutral neutral line that comes through here. I'll draw it as like a dotted line here. The current through that line is 0, very importantly. Okay, the current through that line is 0. Okay, and it comes and it connects to the source somewhere, right? So the delta configuration doesn't really have a nice place for the neutral to go. But if we were in the Y configuration for the source, right? If we were in the Y configuration, then the neutral does have a nice place to go. And so you would say that the loop that this current is going through is now very visible, right? It's that loop like that. Right? And that's like the A loop, right? The A loop, and there's 3 loops because there's 3 faces, right? So there's one loop, right? There's another loop, right? And then there's your third loop, right? And very importantly, notice this middle neutral has all 3 currents at the same time in there, right? And since the currents, so you know that's an important thing, all 3 currents going through. And since the currents are complex numbers, right, which are out of phase with each other by 120 degrees, right, 120 degrees, they add to 0. Imagine adding these vectors together, you would get 0 as your answer. So that's why there's no current through the neutral line, right? So since there's no current there, we don't really have to account for much things that's going on there, but we do use it to create the loops. And so as you can see, we need a turn. I'm going to get rid of the colors. Well, you know, I'll leave the colors on this one, but I'm going to just use the screenshot again for the next one. It'll be a little easier to see. But we need to convert this to the Y configuration in order to get the line current, because we need to create some sort of loop in order to find the current. Right? There needs to be some sort of loop in the circuit. So I'm going to do that. First things first, I need a clearer picture of the circuit. Guess I'll just use the same picture again. I wish there was a crop button. There is no crop. How about I do this? You must convert to from delta to Y for finding the line current. Yes. But we'll look at, there's other parts to the question, right? There are other parts to the question. So we'll see that there are other times where you don't do that, right? But for finding the line current, you need to. Possibly there's another way, but this is how I know how to do it. I don't know every way, but yeah. So let me just take this screenshot so it's not so confusing. There we go. Okay. So before we begin, let me have a sip of my water quickly. Okay. So make sure everything's recording still. Good. To convert this, we want to start labeling things first of all. Oh yeah, and then also determine if it's a positive or negative sequence. I mentioned that, but something distracted me, I guess. So determine if it's a positive or negative sequence. That's an important thing too, because that kind of just changes how the equations kind of work here, right? So the way you look at it is you look at it like this. Well, so from this voltage is going to come first, right? Right? Because it's the highest phase, like the phase angle is the biggest. This is going to lag behind it, and then it's going to be this, right? So I would say that this is going to be we go from B to A to C, right? First, second, third. The order I got from the phase angles, highest one to lowest one, and then the letters I just got from the positive sides there, the positive sides of the voltage source. So B to A to C. That'll be the order of where the peaks go, B to A to C. And I like doing this with A in the center. I like doing it with A in the center because then you can see relative to A, B is ahead and C is behind. Right? I like drawing it like this. It's a little bit better, more descriptive than ACB. Okay, so that tells us it's a negative system. And honestly, this unit has just a lot of formulas in it, but you really don't actually need to use any of them if you can just understand the sequence, right? And that all the things are 120 degrees out of phase with each other. So now that I have that down, now that I have it's a negative sequence, right? I'm going to, what would a positive sequence look like? Well, a positive sequence goes from A to B to C. So it would probably be something like, I don't know. Let's see. Let's see if I can make an example here that actually makes sense. A to B to C. So then that would have to be something like this. It would have to be something like, I don't know, 30 here. It could be 0 there, I guess. 30 here. and this would be 0. A to B, yeah. And then this could be negative 122, I guess. I think that should work. Might not be the best example. Oh no, that can't be 0. They have to be 120 degrees out of phase with each other, don't they? So 30 here, then yeah, okay, so then we can do it like this. 30 here. Shift this ahead by that, so this would be 150, right? This would be 150. And no, would it be 150? That doesn't make sense. Hold on, sorry. Behind, yes, that would be negative 100, negative 90. That's what it would be. There we go. Okay. And then here, this would be, no, let me see if I got that right. Sorry, I'm trying to come up with an example on the spot here, and let me see if I can get it working. Well, I mean, essentially, if this was just negative 120, and this was 120, then you would go C, A, B. Yeah, okay, so that would be a positive sequence here, right? But that's kind of a boring one. I was trying to come up with one. So importantly, they have to be 120 degrees out of phase with each other. Right? That's an important point there. They have to be 120 degrees out of phase with each other always. And then if I, for example, like made this 30, right, then I think all the other angles would have to go up by 30 as well, right? So then this would have to be 150 to be ahead. C is head, yeah. And then this would have to be 90. Yes, I think I was right before. 90, right? And so how you look at this is you just say, okay, the voltage C comes first, right? C, and then comes A, and then comes B, right? And so it's a positive sequence, right? Like this. I don't want to confirm if it's a, yeah, like I guess that makes sense, but maybe they would turn things. I don't know. I don't use that rule personally. I wish I could give you a better answer if that actually is true. So if it goes counterclockwise, it's positive sequence. If it goes clockwise, I mean, yeah, if it goes A B C A B C A B C, yes, that is. I mean, then it's a positive sequence. And if it goes A C B, then it's a negative sequence. Yeah, but I think that I don't know if that's actually helpful in solving the thing. But what's important is just if it's going A C B, or if it's going A, B, C. That's what's important. Hopefully that makes sense. The particular order is really what matters here. Okay, I'll take that as it's okay. So we have a negative system. Yeah, it won't. So someone just said that won't work if C and B are switched in the question. Yeah, I was thinking that too, right? So if they switch C and B, but I don't think they do that. Honestly, I don't think they do that. But if they switch C and B, then that wouldn't work. Saying counterclockwise and clockwise, right? What's more important is going A, B, C or A, C, B. That's what's important. Okay. So now we want to start finding the line currents. So to do that, I need to switch this to the Y configuration. So the Y configuration is going to look like this. Right? Connect that there. Connect that there. This voltage right here, I would say that voltage, right? The voltage source is VAB. I would say this voltage source here is VBC. I'd say this voltage source here is VCA. I would say this voltage source here is, I kind of want to leave some space there, VAN, A to neutral. This is VBN. This is VCN. Just giving labels to everything right now. So again, you can use your formulas here, but I think it makes a little bit more sense to just figure it out from the circuit. What I'm going to do is I'm going to create a KVL loop here, right? I'm going to create a KVL loop to figure out more information about the circuit here. So it's going to be negative VAN plus VAB, right? Plus VBN. Yes. Okay. So equals 0, obviously. Let me just confirm that I did that right. Negative VAN plus VAB plus VBN. Looks right to me. So what I'm trying to do is I'm trying to figure out what VAN has to be. That's the first goal here. And then once we know VAN, and I know the type of sequence it is, sorry, I don't know why I said negative system. It should be sequence. I can just determine the other ones by just shifting everything by 120 degrees. So I just want to find VAN first. So how I'm going to do that is I'm actually not going to solve for VAN in this equation because I do not know what VAB is. Well, sorry, I know what VAB is, but I do not know what VBN is. So a trick that we can do is I can rearrange it to look like this, and you'll see why in just a second. So VAN minus VBN. Okay, so VAB is equal to VAN minus VBN. Okay? Which is a good thing to note. These are all phasors, by the way, right? These are all phasors. But I'm not going to write the line for every single one because it's going to get messy. But they're all phasors. Now, VAB equals VAN. Now, minus. I can replace VBN with something here. What I know is that since this is a negative system, VBN equals VAN just shifted ahead by 120 degrees. Okay, shifted ahead by 120 degrees. Hopefully that makes sense because it's a three-phase system and it's a negative sequence, right? We want to go from A to B, we go ahead by 120 degrees. So how do you shift a complex number ahead? This is a complex number. How do you shift a complex number ahead by 120 degrees? Well, what you do is you take VAN and you multiply it by 1 to an angle 120 degrees. Okay, so this is the action of shifting it ahead by 120 degrees right there, right? That and that. I'll just do it with the pen. That and that are the same actions that we're applying to VAN. And now I can substitute that into the equation here, right? So I'm just going to say side, do it a different color. I'll just say side note here. I'm going to take that, put that in. So VBN is VAN times 1 to an angle 120. Times 1 because I don't want to shift the length of the vector. I just want to rotate it, right? So sometimes you'll see this notated as just VAN to an angle 120, but I don't like that. That doesn't really make sense to me. So I want to multiply it by 1 to an angle 120.
So Adam, could we do the exact same thing, but just isolate for VBN?
Yeah, like could I have made a loop here?
Negative. Yeah, and then shift, or no, do the same sort of equation.
Oh, yeah.
But then just shift VAN negative 120 degrees.
So let's see. Yeah, so VAN is equal to VBN, right? But you want to shift VBN backwards by 120 degrees. So I'm going to multiply it by negative 120. That should work.
Mm-hmm.
Should work. Yeah.
Okay, so you could solve for either variable.
It will work, actually. I can guarantee it will work. Yeah, for sure. I like to do A because A is the first one, right? I don't know. That just makes sense to me, right? But you could do it with whatever one you want.
Wait, if it was a positive system, you would shift it behind 120 degrees,
You
right?
shifted behind 100. Yep, exactly.
All right.
Exactly right. So I'll erase this so I don't confuse anyone. But yeah, that's the idea. So then now I can do this. I can say VAB equals VAN, factor of VAN out, 1 minus 1 to an angle 120. Okay, and we know VAB, that's given to us in the question, and I can use this now to solve for VAN, right? So this complex number here, VAB equals VAN times 1 minus 1 to an angle 120 is going to be root 3 to an angle of tan inverse of 3 over 3, 30. Negative 30. Let me make sure of that. Negative 30. Someone confirm for me. That won't work.
Thought it would be positive because
It's negative.
It's a negative system. So it would give you a, like, if you're in Andy's class, remember how he derived it by drawing like the vectors?
I'm gonna be totally honest. I tuned out entirely at that point. I could not. I could not follow. I could not follow what he was doing.
Okay, then
That didn't.
never mind.
It
I
didn't
guess
really make much sense.
we'll
to
go
me.
with negative 30, and if it's wrong, I mean it's easy to fix because you can easily change the negative angle.
Mm-hmm.
So for converting delta to y, according to the textbook, that is the exact relation, but for a positive system.
This is for a positive system.
Yeah, and I'm pretty sure, like I was working on like the practice midterm before, and you can get the exact same answer if you just change the negative 30 to a positive.
But
I'm not entirely sure
negative
why.
30 in the
Yeah,
from my calculator.
No idea.
1 minus 1 to an angle. So is one of my angles off here? I'm shifting ahead by 120. So I want to go there. And then 1 to an angle, 120, this here. Let me check my notes. I'll check them here.
Oh, what it was, I saw on the midterm. I think it was like minus V and B is what they did. I'm not sure why, but I remember seeing that as well.
They said, sorry, what was it? They did what?
So for VAB is equal to VAN minus VBN. Instead, they did VAN minus VNB. And I'm not sure if that would make a difference.
Oh, I see. I don't know. Yeah, I'm not sure. Let me look at my my notes here quickly. I think so. We are from a delta to y, and we were looking for line voltages. I think VAB equals VAN plus VBN. VAB. No, that should be fine.
No,
VAN
what
minus
Parth
VBN.
said I think makes sense though, right? Because if you take V from A with respect to N, so that chunk plus VBN, you know what I mean? Like
Yeah.
then you're comparing VAN, VBN.
I sent you a picture of what I meant, by the way, or at least why I think it's 30.
Yeah. So VBN, VCN, VAB.
Because you have to do VAN minus VBN gives you VAB, correct?
VAN minus VBN gives you VAB. Yeah. And that would be an angle of negative 30, wouldn't it?
No, so you want to go from VAB up to VAN, right? So you need to
Oh, no.
VAB is larger than.
Yeah, I think I understand. It's that this is not quite this. Sorry, I didn't mean to interrupt you like that. But I think the thing is that I'm going to switch this around, and it's going to be VAB over root 3 to an angle 30. That's my next line.
Yes.
That's my next line here. Yeah, just because I'm solving for this variable here, right? That answers it. Like that.
Yeah. That's what
goes
you
with you're
should
saying?
get at the end, I guess.
Yeah. Yeah, exactly. I wasn't quite there yet. Yeah. Okay. So I think we're good. I think we are. Nothing's wrong. Yeah. So let me explain how I did this. Obviously, I did that really fast.
So Adam, just a quick question.
Yeah.
Imaginary is on the y-axis, right?
Imaginary is on the
Or is
y-axis.
it-
That is correct. Yes.
Okay.
Yeah, that's correct. Okay. So from here, sorry. There's. Let me see. Some people sent me something. Yes. Good. And I'm good. I think. Okay. So. From here, we want to. From this equation, I want to solve for VAN. Right. So in order to solve for VAN, I need to move this complex number to the other side. So the way I just think about it is I'm just moving this times root 3 to the bottom, right? And then this minus 30 becomes a positive 30 here when I move it over. Obviously, there's that's not exactly correct, but if you just want to do it quickly, right, it's just good to say, okay, well, divide both sides by root 3, and this to an angle negative 30 just becomes to an angle 30 over here. And so now we have an expression. VAN is equal to VAB over root 3 to an angle 30. So I think on the exam, if you just go right for the formulas, it's okay. But I think it's very easy to get confused when it's a positive or negative system, and if it's why, what's happening, and everything like that, right? And if you have to answer more questions about it. I think on the exam, it's fine if you just go right to this, because there you can just find the formula in the textbook for this. But again, I think it's more reliable to do it like this, because you know exactly what's happening, why, you know what you've accounted for the positive negative system properly, all that. So now that I have VAN, I can find VAB pretty simply, right? So now that I have VAN as an equation, I can find VAN pretty simply. So VAB is 35 to an angle 0 over root 3, and just times 1 to an angle 30. I don't like to put, it doesn't really make sense to put angles like that together. So you're really multiplying by 1 to an angle 30, right? So then that's just going to be 35 over root 3 to an angle 30. And there we go. So that's VAN. And now if you want to find VBN, it's really no stress. All you got to do is you got to just take VAN, and you want to shift. So shifted ahead. So ahead 120 degrees, right? So you're going to take VAN and you're going to shift it ahead, multiply by 1 to an angle 120. So that's going to be 35 over root 3 to an angle 30, right? Times 1 to an angle 120, which is 35 over root 3 to an angle 150. There we go. So there we go, shifted ahead. And then if I want to find VCN, I want to just take this and I want to shift it backwards by 100, like shifted later by 120 degrees, right? So if it's 30 minus 120 is going to be negative 90. So it's going to be 35 over root 3 to an angle of negative 90 degrees. And so, I didn't have to find, this was not actually part of the question to find this, but I think it's just a good to show here to find, VBN. Once I found VAN, I can find VBN and VCN very fast. Right, from that. But the actual question, yeah, sorry, go ahead.
Yeah, no, sorry. If there is a question, I could go ahead.
No, yeah, you can go ahead. Yeah.
Okay. Yeah, so just right over there, right on your screen, from going from that first line to the second line where you went from negative 30 degrees to positive 30.
From here to here?
What's the ruling on that so that the negative switches sign? Okay,
so essentially what you're really doing, let me just do it the long way here, is you're dividing both sides. So it's really VAB over root 3 to an angle negative 30. So you're really just dividing both sides by that complex number, right? And then from here, VAB, you're substituting that VAB now. Well, VAB is, well, actually, you don't have to actually account for that. We don't have to substitute VAB in yet. It's just VAB over root 3, over root 3 to an angle 0 times 1 to an angle negative 30 equals VAN. And now this, up here, you can say I'm imagining I'm multiplying by 1 to an angle 0 up here. And so these would subtract, and it would be VAB times 1 to an angle negative 30, right, over root 3 equals VAN. And then finally we have VAB over root 3 to an angle 30. That's like the really technical way to do it, right? Is you have to apply these division rules with complex numbers. But I think it just makes a lot of sense to also just say, I'm just dividing both sides by root 3, and the negative angle of 30 becomes positive on the other side there. Same effect.
I think the actual way to do it is to convert it to rectangular form, and then you can see the angle going up, because the imaginary number, it goes up to the top and then it becomes 30, positive 30.
Yeah.
I converted to rectangular form, and I got like positive 30 at the end.
Yeah, so that's another way to do it. This works too because there's rules for dividing with polar coordinates, and this just follows the rules for dividing with polar coordinates. But yes, of course, you can also convert it to rectangular, and you should get the same thing. But I think it's just faster if you just say, oh, well, divide both sides by 30, and this becomes positive. And there you go.
Sorry, could you show what you got for VCN and VBN?
Yeah, VCN is here.
And VBN?
VBN is, here too. That's VBN.
Okay.
Yeah. Okay.
Thank you.
No problem. So, okay, so that's computing the line current through ZT. No, that's not computing the line current. Sorry, we found these voltage. We didn't find the line current yet, but we're pretty close. Could we follow the same steps if it was positive? Yes, for sure. You could follow the same steps if it was a positive sequence. You just would not want to. You want to shift a different way, right? If it was positive sequence, it goes the sequence goes A to B and C comes after, right? So from here, you would want to BN is going to be AN shifted behind, right? Behind by 120 degrees. Go behind. It's later, right? So it would be negative 120 here. And so you have to make changes like that throughout the whole thing. Yes, so negative 120. Yeah. Okay. Now that we have these voltages, right? I know that voltage choice there. I can just I only need one really. So I can imagine my neutral. I can imagine my loop. Right? Just focusing on that loop. The current through ZT, right? Again, I'll just redraw the loop. So the loop kind of looks like this. So we have plus minus, we have our neutral there, right? And then we go like this, and then we go like this, and then we have an impedance here. We have an impedance here, and then we have we go back. Let me just draw it properly. Yeah, and then we go back just like that. I don't know why I drew it so crooked. Sorry. Let me impedance here, and there we go. That impedance is ZT. That's ZL, right? So I'm just drawing this yellow loop essentially. Just drawing this yellow loop. Source ZT ZL, right? And I'm looking for this current, right? So that's not super complicated. I know this. This is VAN, right? I know these two impedances too. So V equals I Z. Yes. So I equals V over Z, right? So V is VAN over ZT plus ZL, right? And I know all these numbers. So VAN is 35 over root 3 to an angle 30. So 35 over root 3 to an angle 30. I'll just I'm not going to answer the phone. And then from here, we just want to plug in our things for ZL and ZT. So ZL, I'll just put it on the screen here so I don't have to scroll up and down all the time. So ZL, well, let's start with ZT, I guess. 15 minus J9 plus 7 plus J14. That's the two values there. And my calculator I can just plug this in my calculator. So let's go for it. 35 over root 3 to an angle 30. Oh, someone's calling again. Let's see. Okay, give me 1 second then if someone's calling 2 times. The phone is in a very weird spot, so I have to reach way around to get it. Okay, good. So then we can continue here. This is 35. Someone text me about it? No, it's like there's the buzzer downstairs, so I think someone's trying to get in. Anyways, 15 minus 9i, okay, plus 7 plus 14i. 7 minus 9i. 7 plus 14. 10 minus. Wow, okay. Typed it in wrong. 15 minus 9i plus 7 plus 14i. Yes, good. So I got 0.855635 plus 0.26479i. So that is going to be 0.896 to an angle tan inverse 0.26479 over 0.855635. Angle 37.134 degrees. Okay. So I think that's what they want as the answer. Just the magnitude. It doesn't really matter the angle because they all have different angles, but just the magnitude of the current is just going to be that. Yeah, I think we are allowed. Yes, we are allowed to use a calculator for a calculation like this. Someone asked me if we're allowed on the test to use a calculator. I mean, I'm fairly certain. Be good to know. But yeah, I think my angle's a bit off. 0.6. Yeah. Yeah. What did I type in? Yeah, 2. Oh yeah. I just missed the 2. Yep. Yeah, yes, you're right. My angle is off. I just typed it in wrong. Thank you for pointing it out. 17.2. Yeah, there we go. What calculator do I have? I have Casio FX 991EX. Anyone's curious? There we go. That's the calculator. Okay, so I typed it in wrong. That's why my angle was wrong there. So yeah. Okay, so there is the line current. Perfect. We did that. Let's try now to do the next part of the question. So I don't know. What do you guys think? Should I complete the this question, or should I have very little time for the Fourier series question, or should I maybe just do one extra part of this and then go to the Fourier series question? What's more important, I guess, to you guys? What do you think? Doing the
rest is just doing the same for IB and IC, right?
Well, not quite. No. The next part is there's different stuff. There's some different stuff. Part B is not super complicated. Okay, so it looks like some people are saying Fourier is important. One extra part and then do Fourier. So for sure we can do that. One extra part and then Fourier. You could just summarize the method used to solve the other parts and then move on. Yeah, sure. I could do that. Yeah, actually that probably is good. I'll just talk about how to solve the other parts and then we can move on from there. So compute the voltage across ZL. What you do to do that is you just do this, actually. Like you just look at the circuit again and you do voltage division. You know the source, you know these two impedances, so you just do voltage division to figure out the voltage across this source. So I'll just say do voltage division. Voltage division, right? From this circuit. I'll just move it here so you can see it. There we go. You know everything. So, any questions about that? Let me know. Next is compute the current through each voltage source. I sadly don't have the final answer. Like this test doesn't have any answers on it. So, but I'm fairly confident we're doing everything right. Compute the current through each voltage source. A little tricky. So let me see how I did it here. This is what I was talking with people about earlier. So the current. Okay, the current through each voltage source. This is how we do it. We might do this one actually. It's kind of hard to explain this one without doing the circuit. So usually they specify what configuration. So the current through each voltage source in the well, actually, sorry. If they said in the Y configuration, then that would just be these currents. Well, not these. Sorry, these voltages, right? Which you could then use to find. Oh, did we not find the currents? No, we did find the currents. Yes, we found the current there, right? So this is I1, I would call it, right? I1. So from the Y configuration, right, going here is I1. There's sources, right? So here's I2, and here's I3. So if they said from the Y configuration, then it would just be these, right? So I2 is going to be 0.896. I2 is the B, right? B is ahead of A, so I want to shift this ahead, so to an angle of 100 ahead by 120, so 137.2 degrees, and I3 is 0.896 to an angle behind I1 by 120 degrees, so 17.2 minus 120, I get negative 102.8 degrees, right? So if this question said compute the current through each voltage source in the Y configuration, these would be the answers. Because it's just you can see like in this here, it's just that's what it would be, like that, right? Like I guess if you look at it, maybe it's better to see in this circuit, right? It's the same as these currents, just through the voltage source. But in the delta configuration, it's a little bit different, right? That's not the same current, right? Because if you look here, if we were to focus on like up here, this current, right? We know there's a current here, I1 leaving, right? And then we would have IA like this and IB going like that, right? Or IC, right? So this is the current going towards A, current going towards C, right? That's how I would describe it. And then this would be IB, right? So if I wanted to find IA, IC, IB, these are called the phase currents, I'm quite certain, right? Let's see how we would do that. So I'm going to do nodal at this node right here. Let's say I'm looking for IA, right? So I'm going to do nodal at that node, leaving as positive. So it's going to be I1 plus IC minus IA equals 0, right? From here, I can say, okay, I1 equals IA minus IC. Okay. Again, we're going to do kind of a similar trick here. IC is going to be behind IA. Well, let's see. It's going to be behind IA by 120 degrees because it's a negative sequence. So I can write this as IA minus IA times 1 to an angle negative 120. Yes. Okay. And once again, I can just do this. And this is because IC is behind IA by 120 degrees. So this will let me find IA, right? This is going to be a nice method to find IA here. So 1 minus 1 to an angle 120, negative 120, sorry, is going to give me IA times root 3 to an angle 30, positive 30 this time. I1. And now to solve for IA, I'm just going to bring everything to the other side. This is going to be I1 over root 3 to an angle negative 30 equals IA. I know I1 from my previous sections, right? I figured out I1. So I can just do that, substitute that in here, right? And that'll get me IA. So let's do it quickly. Okay? I1 is that, so 0.896. So I'm going to just put that here. 0.896 to an angle of 17.2. Okay? Over root 3, and then really multiply by 1 to an angle negative 30 degrees equals IA. So the things are going to divide. So 0.896 over root 3 is 0.5173 to an angle of 17.2 minus 30. Right? 17.2 minus 30 here. Minus 12.8 degrees equals IA. Okay, and so we figured out IA through that. Again, it's a similar process. You just sort of make an equation using KVL or nodal. So KVL for voltages and nodal for the currents. And I guess I should call it KCL, but whatever. Then you just look at how IA and IC or VAB and VAN and VBN, they compare in some way. They're very similar, right? But they've just been shifted. And we're going to use that to help us solve these certain questions here. They've just been shifted by 120 degrees, either ahead or behind. And so that's depending on the sequence is very important to be able to tell at the start. So we found IA. To find IB, IC, we just shift them, right? So IB is ahead of IA, right? So it's going to be equal to 0.5173 to an angle of, well, I'm going to add 120 degrees to this. So it's going to be, I don't want to make a mistake. So 12.8 plus 120 is going to be a nice 107.2 degrees. And IC is 0.5173 to an angle of, so negative 120.8. This time for IC, I'm going to subtract 120 because we're going to be going, like, IC is behind IA. Wait, this time wouldn't I1 be multiplied by 30? By positive 30? Let's see. This seems to make sense. Like, are you saying this should be a positive 30 here? Put this in. 32.8 degrees. Is that what you're saying? No? Good? Okay. Okay. Sounds good. So from here, from here we figured out, we answered that part of the question too. Compute the current through each voltage source. There we go. And then find the total complex power is the last part of the question. Find the total complex power produced by all these things. So produced by the voltage sources. So complex power is essentially calculated by doing, so I think it's S, I think that's the symbol. Or maybe it's Q. I should find that. Don't get it wrong. And just stay consistent with the things. S? Yes. Okay. It's S. So S is equal to V times I complement. So the power produced by the voltage source is going to be the voltage, right? Times the complement of the current through it. And actually, sorry, 1/2 of that. 1/2 of that. Sorry, divided by 2. Right. The recording will be posted. Yeah, I will post it on my YouTube, and then I think Christine will post it somewhere too. I don't know, but yeah. So the that's how you calculate complex power, and I'm fairly certain it doesn't matter if you use. Sometimes we need to convert to RMS value. Do you know when we do that? So you don't convert to RMS value here. You don't need to convert to RMS value. I don't think. Well, you don't need to. if you convert it to RMS value, there's no divide by 2. So if for some reason they give us on the test RMS values, when you're calculating complex power, there's just no 1/2 in the front. Okay, but since these are not RMS values, we have this here. So maybe someone said you have to convert. It's still conjugate. Yeah, everything else is the same. Yeah, but it's just the 1/2 is there if it's not RMS. Okay, and then you just do that for each of the sources. The voltage across it times the current through. And then add it all together. 3. So you're gonna have 3 of them, right? You can have 3. You add the 3 together. So I think just, we're already ahead, after the time, but we can still do the Fourier question. I have not a super amount of time, but let's see. I'll try my best. So let's see how much we can get done soon. I have, I guess, maximum about 15 more minutes that I can go for. So let's try to get that done. So let's go to the Fourier question. I got to open it up here. Okay. So we have this. So the Fourier question, given this, given the periodic non-sinusoidal voltage Vs shown below, find the fundamental frequency omega 0 of Vs. Okay, so that's obviously not the whole question, but that's just the start. So Fourier stuff is very useful for, again, periodic stuff, but they're not sinusoidal, but we can approximate it by sinusoidal things. So you want to identify a period first, right? So one period looks like that, right? Omega 0 is 2 pi over the period, always. It's always 2 pi over the period. So omega 0 is going to be 2 pi over 2, which is pi. That's it for part A. Part B, Part B is find the DC component of the Fourier series. They really miss the word the a lot in here. Of the Fourier series, A0 for Vs. Okay. So to compute that, it's really the average value, but I think it's just best to just go right with the formula. So it's 1 over the period integral over the period of the function dx, or I'll say t dt, or it's actually s, I guess. S ds. I don't know why they have an s here. So no, never mind. They have a, sorry, that's the t in seconds. What am I talking about? Yes, so t axis. So that is 1 over 2 integral 0 to 2 of f of t dt. So, well, what's the integral from 0 to 2 of f of t dt? It's just the area under this curve, which is 5. 5 times 1, right? So it's 5. So this is equal to 1/2 times 5, which is 5 over 2. That's it. That's your component like that. Okay. Find the coefficient. Obviously, ask questions if you have questions, but yeah, that's it for that. Find the coefficient for the cosine component of the Fourier series an. All right, an is 2 over the period, integral over the period of the function, right? Cosine n omega 0 t dt. A little bit different than the math way. Honestly, the math way, like obviously this is the same Fourier series. There's no 2 Fourier series, but the way we do it in ELE is honestly a lot simpler of a way to do it. You really just follow these formulas. Let me just, you literally just exactly follow these formulas. There's no like other complications that we deal with, at least in this course, right? You literally just follow exactly these formulas here, right? And I like that it's n omega 0, so it's like some sort of multiple of a fundamental frequency. And so otherwise you just follow these formulas. So anyways, this is 2 over 2 integral 0 to 2 of, I'll still leave it as f of t cosine n omega 0 t dt. So that's just 1. So now 0 to 2, let's look at our function here. 0 to 2, well, all I really care about is 0 to 1, right? Because 1 to 2, it's just 0. So I can break this up. I can say this is the integral from 0 to 1 of f of, well, of something, and I'll write that in a second, dt, right? Plus the integral from 1 to 2 of something dt. Right, first of all, just make sure you're comfortable with that I'm allowed to do this, right? I can break up the integral into 2 different ranges. From 0 to 1, our function is 5. So I can just literally write 5 cosine n omega 0 t. how bald it is was he found the symmetry, and using that you can just say a at or b equals 0 right off the bat, just like in math. Yeah, so definitely you can do that. You can look at the symmetry. I'm gonna go through it just because we want to a little bit practice breaking stuff up like this. But yes, you can definitely see from symmetry. Although this one's neither, because you can't reflect it across the y-axis, and you also can't reflect it across this line like this. Unless you can? No, you can't reflect it. I think it's neither. No, is it neither? Yeah, it's odd. But odd would mean that you can reflect. I'm trying to remember. Reflect across. You reflect across this. Oh yes, but then you ignore the DC component. Yes, that's the thing. Okay, so we don't have to talk about it too long. Yes, but you ignore. So the DC component is this like average value. Imagine shifting this then down, right? Shifting this then down to go like this, right? It would kind of look like that, right? And then it's more obvious here that it's going to be an odd symmetry because it kind of looks, right? It kind of looks like a sine curve, right? It's gonna, approximately, very approximately be a sine curve, right? And sine's definitely odd, so it goes like that. But again, you don't need to consider that. That's the thing. You don't need to consider that. So if people are struggling, honestly, just go right for the formulas and then go for it. This component there is just 0, right? From 1 to 2 is just 0 cosine of n omega 0 t dt. So this whole integral goes away. And all we're left with is 5 times the integral from 0 to 1 of cosine of n omega 0 t dt. Okay, which is 5 times 1 over n omega 0 sine n omega 0 t evaluated from 0 to 1. Right, so in a second I'll substitute in the omega 0. Right, so 1 over n omega 0 sine of n omega 0. And I don't even have to account for the 0 because sine of 0 is 0, so it just goes away. I'm going to now substitute in omega 0. Omega 0 was pi, so it's 5 times 1 over n pi sine of n pi. Sine of n pi is going to be 0. The whole thing is going to be 0. So an is equal to 0. Okay. Fantastic. Bn, right? Bn is going to be 2 over the period, integral 0 to the period of f of t sine of n omega 0 t dt, right? Which is going to be, well, I'll do this a little bit faster, right? So that's just 1, and then I don't care from 1 to 2, so this is just the integral from 0 to 1 of 5 sine n omega 0 t dt, right? Which is 5 times negative cos, negative 1 over n omega 0, cos of n omega 0 t, evaluate 0 to 1. And then we put in 1, and then we put in 0. So it's going to be 5. Yes, it is crazy how much ELE was learned in 2 days. Negative 1 over n omega 0, cosine n omega 0, plus 1 over n omega 0. Cosine of 0 is 1. We're left here. I'm now going to put in my omega 0. So 5. I'm also going to factor out a 1 over n omega 0. So 5 over n pi negative cosine n pi plus 1. 5 over n pi, 1 minus cosine of n pi is just negative 1 to the n. So there we go. So there is our Bn. I did that a lot faster, so if there's any confusion, let me know. Then from here, we just want to write our Fourier series. So our actual Fourier series, f of t, is going to be the DC component, 5 over 2, plus the sum, n goes from 1 to infinity, of Bn sine of n omega 0 t. And I can just obviously substitute that in. So 5 over 2 plus the sum, n goes from 1 to infinity of, so I'm going to move 5 over pi to the outside here. and then I'm just going to have 1 over n, right? 1 minus negative 1 to the n. I can do that, right? Yeah, I can do that. Sine of n omega 0 t. If an wasn't 0, you would have a square root bn plus. Yeah, okay. So what you're saying is you want to convert it to the amplitude phase form, which is yes, that is true. So sometimes you have both, right? But you still only want to write it as, you know, cosine terms or something like that, right? Just cosine terms, but shifted maybe, right? You don't want to have also sine terms in there. So what you would do is you'd write it in amplitude phase form. And so if I go to my notes, I can just show you the formula for that, right? So you would write it like this. Now, of course, an is 0 in our case, right? So you can't really, right? There's no components like that. But yeah, you would write it like that essentially, right? So an is just that. Theta phi n is just that. Negative in the front is on purpose. You can just write this as 10 over n pi for only odd ends, right? Oh, yes, because why 10? 5?
Because you end up, if it's 1 and then the n ends up, like if you get 1, wait, why you have 1 minus? Isn't it negative 1 minus 1? Oh wait, no, never mind. Sorry, yeah, the negative goes there.
Negative goes there. What the solution was, they made a table by subbing in numbers for n. Yeah, like to simplify this. Yeah, you can simplify this, and then you see the pattern. Yeah, but you also don't have to do that, right? You can also just leave it like this. Why make it more complicated? Because when you use odd ends, then there will be negative 2 inside the brackets, which you multiply. Oh, yes, okay. There was an odd end, so if it was like a 1, so then it'd be a 2 inside the bracket, you multiply it out as 10, yeah. That's true. There is a pattern here with some other, you can write it a different way, but I think it's okay. We can leave it. We can not do that, right? It's fine like this. I think what they mean by 1 mark for simplifying is turning this into this. Like turning the cosine stuff and the sine. Don't leave the cosines and the sines in there, right? But I think past that is you don't have to. I think.
I mean, in the solutions they made like the further simplification, like they wrote bn equals 10 over n, I think, pi n, and that's like 1 mark.
Is it? Yeah,
For
really?
n equals 1, 3, like when n is odd, if bn is 10 over pi n, and then like if it's even, if bn is 0, like that part they put it as 1 mark, but I'm not
I
sure.
see. Interesting. Okay, I'm not sure. Yeah, I'm not sure how it's gonna be. I would have thought they wouldn't do that, but yeah, I don't know. What time is it? Okay, I really only got a couple more minutes left, so let's try to see, you know, how would we do it if, let's say, most likely on the circuit itself, they are going to just ask, find the coefficient, they're just going to ask us to use the first couple terms. I think Andy confirmed that it's going to just be the first couple terms. They will not ask you to do it like in full generalization of n, right? So let's say that this, you know, asked you to say, okay, if Vs is fed, or does fed have one word? Yeah, fed has one. Okay, whatever. Through the following circuit, calculate the response VO using the first 3 terms, right, of f of t. I'm quite certain he confirmed that we're going to just have something like that. So f of t would then be, okay, well, 5 over 2 plus the first 2, the next 2 terms, right? So it's going to be, I'm going to have to see this, so it's going to be 5 over pi times 1 over 1, negative 1, 1 minus negative 1 to the 1, right? So 1 minus negative 1 to the 1, and then sine of omega 0 t, right? Sine of omega 0 t. Omega 0 is pi, right? Pi t. And then our next term, well, our next term is actually going to be 0, right? So let's just say for this term, it's going to be, we'll just count that. Oh, actually, I can't count that. So I can't use, oh, never mind, I can. What am I talking about? Sorry. This is going to be 5 over pi, 1 over 2, right? 2, because 1 over n. 1 minus -1 squared sine of 2 pi t, right? But the thing is that this is 0. Whoops. Is that this is 0 here, right? Whoa. Don't know what's going on there. That is 0. So the whole term goes to 0. So let's just simplify these first two terms here. So 5 over 2 plus, so this is going to be 10 over pi. 10 over pi sine pi t. And then so from here, to figure out the VO, all you would do is you would just do superposition in this case, right? You would use this, you would use this here, and then first as your DC source, and then you would calculate VO from there, and then you would forget about that, just use this, and now it's going to be an AC analysis, and so we want to do that here and calculate VO again, and then if you had another term, you would do it again, and this time it would have a different frequency, which is important, a different frequency every time. 0, frequency pi. Next one would be frequency 3 pi in this case, and then 5 pi, right? Because we can only do the odd ones. So if they said first 3 terms of the series, do we also include DC as one of the first 3 terms? They'll be more specific, I'm pretty sure. They'll say the DC term and 2 cosine terms or something like that. I think so. They will ask that.
When you see the DC term, it's 5 over 2, right?
5 over 2 is the DC term.
Okay.
Yeah. For some problems, they convert n equals to 2k plus 1. So yes, someone was just saying, does a 0 term count or no? They probably will also explicitly say that as well. But I'm fairly certain we won't get one with a 0 on there. I don't know if this one turned out to be 0, but yeah, they'll be specific. I hope. So some problems they turn n equal to 2k plus 1. Yeah, because essentially, right, I'm skipping the odd ones. All the odd ones are 0. You don't have to do that, right? Every odd one will just be 0. But if you just want to include only the non-zero terms in your series, you only want the index variable, like this is the index variable, to be odd numbers, 1, 3, 5. And so 2k plus 1 is odd for any k you choose, any integer k. Right? But you don't have to do that.
Wait, will the odd ones be 0 or will the even ones be 0?
The even ones will be 0. Sorry, I probably missed.
Oh, okay.
Yeah, the even ones will be 0. The odd ones are what you want. They will not be non-zero. But the same thing counts. So yeah. This would be the next one. I just brought this here just because that would be the next one, right? And then the next one is going to be 10 over 5 pi sine of 5 pi t. And so you could include however many terms you want if they don't tell you, but they're going to tell you. And then again, you just do nodal analysis. You just do superposition, and you just find all the different ones there through that. And
So
get different
when
analysis
you're
every time. Yeah.
so when you're dealing with 5 over 2, the capacitor would disappear, correct?
Yes. It
Okay.
wouldn't disappear. It would be an
Sorry, it
open
would become short.
an open circuit. Capacitors are open circuits to DC.
Oh, okay. So
Right,
then that
which-
mean that would be 0, correct?
Yeah, it would be, the voltage would be
Oh,
0. Yeah.
okay.
There's no current because there's no current.
Yeah.
going through it, right? Okay, guys. Well, sadly, that is my time. I have something at 8:30, so I have to get to that. But I hope this was helpful for everybody. We went through a lot of stuff. Let me know if you know how it went. But have a good night, everybody. I'm here for a few more minutes if you have any more questions. But once again, thank you guys for coming. Thank you so much, guys. Have a good night.
Recording stopped.